0400 hours. The duty officer of the IAP command post receives a transmission, ordering him to prepare his forces and organize immediate combat readiness.
This is the command center with a warning conference. Stand by.
The display for east is medium.
His subordinates, despite their reduced staff structure, waste no time switching on their equipment and reporting the readiness of each subsystem.
Radio Technical Battalion, ready for combat operations with all subunits.
Противовоздушной обороны связь должна обеспечить оповещение вооруженных сил.
Within minutes, the regiment has come alive with short bursts of communication and the anodyne buzz of cathode ray tubes. Each battalion commander, having received a comprehensive readiness report, contacts the formation commander above them and reports.
Battalion clear at readiness number 1.
The regimental commander arrives, relieving the unit's skeleton crew with the rest of the formation's personnel. The duty officer, having caught up with his commander, relays what he has been told about the condition of his battalions. As the regimental commander is brought up to speed, his chief of staff instructs the PV operator to begin entering the readiness of the formation into Argonne. From here on out, transmissions to the division will be managed without human input by the computing complex. Having taken a seat, the regimental commander evaluates the wider situation in the air. His most trusted advisor, the senior navigator, offers recommendations as to how he could approach the coming battle. He is provided with the direction of the raid, the number of targets, their altitude, and if electronic warfare is expected or actively being employed.
For target 01 and 02, perform preliminary navigational calculations.
The senior navigator rushes to the VDM-1 console to inform Argonne of the task at hand. Almost immediately, a series of scenarios are generated and presented to the commander. He likes what he sees.
For target 01 and target 02, conduct UBC operation.
With a few keystrokes, the combat mission is automatically transmitted to subordinate guidance posts.
The enemy is conducting an attack from the west by multiple aircraft at altitudes of 3,000 meters. Ensure timely detection of targets.
As the raid gets within range of the formation's radars, radio technical battalions assign priority targets and designations to each aircraft detected.
Volga, detect target, azimuth 270, range 110 kilometers. Composition, 4 aircraft, altitude 3,000 meters. Perform identification of targets.
The commander's chief of staff tasks the regiment's guidance officers. Operating on instinct, his hand drifts to the telephone across from him. Before making contact with the TA-57, he pauses and glances at the plotting board flanking him. The display appears unusually beautiful, The tiny contacts drifting across the screen, limned by a soft green incandescence, look almost like a busy night sky. But he does not have time to appreciate the stelliferous presentation before him. Picking out his targets, he recalls a guide to NATO air power given to him in his second year of university. These are Eagles, carrying AIM-7s. It would be suicidal to engage the enemy head-on. If this attack is to be thwarted, it is essential that he relies on two key advantages. They are operating in his airspace, and the knowledge he has as to their probable course. Building atop Argon's suggestions, the unit commander and his chief of staff agree that multiple flights of MiG-23 should be sent on a course maximizing the likelihood of ambushing the enemy from the rear hemisphere, only after they have been degraded by surface-to-air missiles. The expectation is not that these aircraft will stop the attack. It is unlikely that such a large raid could be thwarted by just 2 squadrons. Instead, the intention is to maximize the human and material cost of this action, making it known that any further attempts to penetrate Warsaw Pact airspace will be met with similar resistance. Picking up the phone, he vacillates only for a moment. He cannot take any chances. The Fighter Aviation Regiment is instructed to scramble 2 squadrons, or 10 flights, of MiG-23s. They will advance at low altitude, before climbing to meet the enemy at a distance of 25 kilometers.
It's been said that a war in Central Europe will be decided within the first 5 days. Air power will determine the outcome, according to the experts.
Witness the combat posture. Flying on course. 0508, are you observing?
Observing. Closing in. 0508, everything is registered. Players are registered.
As the flight departs from the airfield, the combat control officer makes a general announcement to all relevant parties. They are one of many flights moving to intercept the coming raid, and all of them must be accounted for. The index of each pilot within the flight is entered into the PV data input console, so that Argon can display its course on the HZBD board. As they climb to altitude, the flight appears on APN-1M, prompting the guidance officer of their native control point to report.
Observing, 560.
The combat control officer authorizes ground-controlled intercept and hands the aircraft off to the navigator.
560, 5th channel, contact with Volga.
5th, 560 on the 5th channel.
Now that the aircraft are in the hands of the regiment, the chief of staff is contacted and notified of this development.
Controlling, 560. 560, proceed by instrument.
Having done everything they can, the battle is now in the hands of the interceptors, heading to meet the target.
Rising to meet the target. Rolling.
Exactly. 560, destroy rolling ahead in a second.
It is a fight to the death.
Understood. First target burning.
Red.
Right away. Red. Away.
The formation was fighting against the clock the moment they gained altitude. Despite the wall of electronic interference targeted towards the enemy, it is impossible to entirely ablate detection. A rapid exodus from the area, back into the division's SAM envelope, is their only hope of preventing retaliation.
Guided by radars, the MiGs head for home. Half an hour later, the landing gears extend and they land in a stream, braked by their drag chutes.
Vozdukh-1 is an especially fascinating system, due to its obscurity. The number of secondary sources which so much as mention it by name can be counted on one hand. Documentation regarding the complex are impossibly difficult to come by, and are usually broken into so many manual series that it is difficult to determine what is relevant and what isn't. The computers developed specifically for it are so classified that almost nothing has been written about how they came to exist. You would think that something so poorly documented would be largely irrelevant. Surely if it was of great importance to the technical development of the Soviet military, it would show up beyond footnotes of footnotes. But you would be wrong. Vozdukh-1 was the first in a long line of advanced ground-controlled intercept systems, which spilled over into automated command platforms across the armed forces. It was a pioneering force that effectively began the long romance between the Soviet military and the computer, and yet, it is forgotten. This video aims to solve that problem, and tell the story of a device that nearly led to the creation of the internet, put computers in space, and changed Soviet aircraft development forever.
Luftangriffsmittel ist unter den heutigen Bedingungen eine aufwendige, komplizierte und notwendige militärische Aufgabe.
To understand the importance of GCI, one must understand the reality of what the situation in the air would look like during a Third World War. Firstly, air defense in Europe would be extremely complex. The saturation of surface-to-air missiles would be so great that neither side would be able to reliably interdict one another without significant losses being incurred. This applies to both sides, but it is especially grim for NATO, who would have to deal with a significant number of unique systems, all operating in tandem with overlapping coverage. This is by no means to say that the USSR and its allies will not struggle to penetrate Western air defense. To give an example, this is what it would look like to fly over 1st Army Corps. While flying low to the ground helps to reduce the threat posed by long-range SAM systems, it does not prevent one from being engaged by manpads, anti-aircraft artillery, and other short-range weapons designed for low-altitude engagements. Much of these systems are placed forward and would be encountered well before Hawk, 2K-12, or 2K-11. These SAMs, optimized for medium-altitude targets, are placed in such a way that flying within their engagement envelope is effectively impossible without being destroyed. On both sides of the Iron Curtain, they are intended to intercept opposing aircraft after they have made it past the previously mentioned threats, as anything that hopes to evade them with altitude would be immediately fired upon. It is for this reason that any operation in the air would seek to target objects that make the risk worth the reward, primarily exceedingly valuable strategic assets. These large-scale breaching maneuvers would involve a huge number of aircraft, and would be the primary application of anti-radiation missiles, as there were more radars in Europe than NATO and the Warsaw Pact's combined availability of these munitions. The necessity of carving out corridors using huge surges of air power would reasonably justify their cost. I need to reiterate once again that it would genuinely be suicidal to do anything less, and both sides generally agreed on this principle. The need to manage this impossibly complex battlefield on the ground and in the air made many conventional solutions to this problem obsolete. No human being could reasonably process the amount of information and have been able to make sound decisions on top of it. Even large groups of people all working together did not possess the capability to effectively manage these assets, especially the burden of collection, assessment, transmission, and coordination with those actively engaged in the fighting. What the Soviet military needed was a series of command and control systems to automatically coordinate aircraft and surface-to-air missiles, while also providing a complete picture of the battlefield so that said sound decisions could be made. These concepts became very clear with the formation of the anti-aircraft missile troops in the mid-50s. Units operating S-25 were at this time coordinated mainly from central command posts. These command posts were not mobile, and neither was S-25. This was generally acceptable as they were deployed around priority targets like Moscow. It soon became clear that the need to move these missiles was of great importance, and with the adoption of S-75 and its low-altitude counterpart, S-75M, finalized by the end of the 50s, and with new SAM systems on the way, that being S-125 and S-200, it was becoming clear that coordination between these assets would be difficult. By 1961, with the S-200 being accepted into service, there began to exist fewer and fewer homogeneous anti-aircraft missile battalions. When these mixed battalions trained to thwart air attacks featuring 2 to 3 air targets per minute, they seldom succeeded. Luckily, in 1957, Me-5 had already begun work on a solution well before this problem had revealed itself. This solution sought to introduce a computerized system capable of assessing the productivity of each radar station attached to a unit, streamline data obtained by low and high altitude radars, and display all of this to commanders, who would then make informed decisions. This complex would also allow for the rapid transmission of data between formations so that a real-time picture of the battlefield could be obtained, allowing for certain threats to be prioritized over others. ASURK-1, as it was known, officially began development in April of 1960, and would receive much of its information from P-80 radars deployed by the formation it was attached to. This allowed for 10 targets to be tracked simultaneously by each radar cluster. Up to 8 battalions would receive these targets in real time. It was adopted in 1963 and would later go on to receive up to 5 firing channels when paired with S-200 battalions. Alongside ASURK-1, NE-5, following a decree issued April 3rd of 1953, began work on what was described as a comprehensive automated system for warning, control, and guidance of interceptors against enemy aircraft. The project was led by Colonel M.I. Mikhailov. Sources are divided on if Vozdukh-1 passed state trials in 1956 or entered service in 1955. A mobile variant intended for closer use to the front, designated Vozdukh-1P, was introduced alongside the stationary variant, which was for use within the USSR. This was developed by A.A. Lvovich. At this time, the P-30 was the most advanced radar that could interface with the new command system. This had a significant impact on the development of Vozdukh's data processing equipment. The P-30 used two antenna beams inclined at 45 degrees to the plane of rotation to derive altitude. This information was obtained from the azimuthal displacement of the target mark between the main and auxiliary antenna beams. This mandated the introduction of a second screen to receive signals from both antennae, resulting in the final product featuring one display depicting azimuth and range while another showed range and altitude, represented as azimuthal displacement. To harmonize information gathered by this new data processing system called the USD with friendly fighter aircraft, a device known as Cascade was introduced to provide all three spatial coordinates. Experimental models coupling the USD with Cascade successfully transmitted encoded commands to fighter aircraft sometime around 1957, which is when they began to be mass-produced as a part of Vozdukh. What is most interesting about Vozdukh-1 is that while it technically entered service in the 1950s, this date is somewhat deceptive, as Vozdukh-1 is a system of systems that was not actually completed until the early 60s. The first, most rudimentary iterations of the complex were designated VPT-01U and VPT-02U. They could only receive radar data, display azimuth, range, and altitude, track targets and friendly aircraft semi-automatically, and transmit this data to higher formations to create a somewhat comprehensive picture of the battlefield. This was still impressive, but not what Vozdukh set out to do. It wouldn't be until 1963, with some sources stating 1965, that Vozdukh-1 was truly complete. This was when VPT-04 entered service, which integrated Lazur, Cascade, ASPD-1, and Kliech. Vozdukh-1 was entirely analog, but would eventually see a complete digitalization just 10 years later, significantly increasing its capabilities. The concepts proposed to make maximal use of Vozdukh's early adoption are interesting to say the least. Between 1958 and 1960, Mikoyan was busy designing what they described as an unmanned interceptor. It was designed to destroy aircraft carrying cruise missiles and strategic bombers, and was designated R-500. It would be prepared underground, before being launched from secluded shelters to defend Soviet airspace. It would then fly at an altitude of 20,000 meters at a speed of Mach 2.5 before locating the target with assistance from Vozdukh-1. It was eventually determined that an unmanned interceptor would be no more effective than conventional manned aircraft, so the program was terminated. The E-150 series were eventually deemed insufficient, especially at high speeds due to the limitations imposed by their fuel capacity. As a result, OKB-155 got to work developing a new aircraft which would receive much of its information from the ground. The C-155 program was created, intended to provide an aircraft that could repel massive raids made up of enemy aircraft and cruise missiles flying at speeds of 2,500 to 3,000 kilometers per hour, at altitudes of 27,000 to 30,000 meters. This led to the development of a new aircraft using E-155P as its basis, which was an experimental interceptor armed with K-9M short-range missiles developed for the E-150 series. To link the C-155 complex with Vozdukh-1, and to determine guidance methods that would be employed on the ground, a commission was appointed under the leadership of V.A. Zarkov from OKB-155, with participation of N.N. Zavidov. 1 month later, another decree was issued, in February 1961. The government stated that Mikoyan was to develop and submit proposals using this new interceptor as a reconnaissance aircraft. There were even considerations for this system to carry a drone that would break off and transmit data at ranges around 1,000 kilometers. Vozdukh-1 is the umbrella designation for the multitude of systems that allow it to function. The subsystems grouped under the Vozdukh name are as follows. ASPD-1 is a ground data link system, which handles the transmission of acquired targets and the display of this data to the system's operators. Cascade is an analog computer designed to provide intercept equations to fighters using data collected from local radar stations or from distant units operating ASPD-1. Lazur is the air data link system, which talks to Cascade. It facilitates the automatic transmission of commands from the ground to the aircraft equipped with the system, receiving course, speed, altitude, range to target, turn commands, target designation commands, and engine afterburner engagement commands. It also handles the transfer of control from one command post, known as a guidance point, to another throughout the course of a flight. Cleach-1, or K-1 as I will be referring to it as, allows for the entire Vozdukh system to communicate in a more traditional fashion if the data link system is not functioning. It's made up of subsystems like K1A, which is a telephone and switching system, KUNVS, which is a series of ground and air communication devices, which allows for traditional vocal commands to be given to fighter aircraft if Lazur is experiencing issues, and K16, which is a data link set. These elements come together to allow for the expedient acquisition of targets, the automatic transmission of this information to all relevant battlefield elements, the provision of an accurate, comprehensive report as to what the battlefield looks like to the system operators using the data it acquires, early warning if an enemy formation is detected, and guidance of aircraft to intercept these formations, with most of these steps being entirely automatic. Vozdukh permeates every level of an air defense formation. Radar companies, both high and low altitude, subordinate to the unit, obtain data essential to the command and control process of assets both on the ground and in the air. This is economically very efficient, as it ensures that aircraft regiments and surface-to-air missile units do not have to operate their own independent radars. This also significantly increases the speed in which information can be exchanged. In an air defense division operating the system, a radio technical brigade consisting of 6 to 9 radio technical battalions and 12 to 18 low-altitude radar companies present and coordinates the entire formation. On average, 2 low-altitude radar companies are attached to each radio technical battalion. The radio technical brigade spreads its subunits across a wide area to maximize coverage. Low-altitude companies are equipped with 2 P-15 radars, but they can also interface with P-12 on the edge of the formation's coverage. Combined command posts coordinating surface-to-air missiles, fighter aircraft, and units-attached radars are considered to be the most efficient. Ideally, all radio technical subunits are equipped with automated means, but this is not always the case. The formation's command post is often placed in the center of all of its deployed subunits, and is equipped with ASPD-1 and K-1. It will always be accompanied by a radio technical command post, which is placed nearby. Guidance points for aircraft are deployed alongside each radio technical battalion. These command installations are equipped with ASPD-1 and Cascade, as well as K-1 for the purpose of communication. Radar companies integrate with surface-to-air missile command posts. Here, ASPD-1 is present. This is the case for both low and high altitude radars. If an air defense formation is armed exclusively with Vozdukh-1P, which is the mobile frontline variant, low-altitude radar companies will usually operate manually without automation. Vozdukh-1P functions very similarly to its stationary counterpart, with the primary difference being that all of its equipment are located inside mobile trailers instead of dedicated command facilities. When Vozdukh-1P first entered service, there was not enough automation to go around, in the form of ASPD-1 and Cascade, and so there were many formations that were operating in what was known as a reduced automation fashion. Here, data to the command post of the air defense formation from its subunits was carried out manually. Automation was primarily employed when available for guiding aircraft to their targets. Later, as more systems were delivered, formations became completely automated, which allowed for the collection and transmission of data from radar companies to be streamlined significantly. Vozdukh-1P equipped formations usually deploy radio technical battalions 180 to 200 kilometers from the command post, which is similarly a centrally located asset. Even when automated, radar companies are generally encouraged to transmit information manually to the command post of the radio technical regiment they are attached to, saving their automatic transmission for combined fighter aviation and radio technical battalions. Non-automated companies transmit data directly to the radio technical regiment and no one else. Vozdukh-1 equipped units are far more survivable when compared to their field counterparts with Vozdukh-1P, as command posts are always located underground in hardened shelters. Alternate command posts are always present to increase resistance to electronic attacks, or nuclear weapons detonation. In combat, radio technical battalions collect and process information from their own attached radar stations, and those of units subordinate to them. Using ASPD-1, this information is transmitted to the Air Defense Formation's command post, as well as the surrounding surface-to-air missile regiments and neighboring radio technical battalion command posts. This information is then processed at the formation's command post and displayed on plotting boards. Subordinate units and subunits of the radio technical formation are provided with warnings and associated information in an automated manner using ASPD-1. If the data collected by the formation is serious enough to warrant a warning being issued to National Air Defense Command Centers, it can be delivered automatically. In both cases, either stationary or mobile, the guidance of fighter aircraft is most often carried out at the Fighter Aviation Regiment command post and guidance points. In certain cases, the formation command post can guide aircraft, but this is only for emergency application and would never be standard. ASPD-1 is by far the most complicated system present in Vozdukh-1. I will do my best to break down all of its individual components and the roles of everyone expected to operate it, and then go through the actual process in which it transmits information and what that looks like internally. The primary coordinate acquisition indicator, or the ISK, is used to acquire targets and transmit their coordinates. It also identifies the affiliation of all aircraft displayed. IPN, or IPN-1, also known as the primary indicator for altitude and digit input and transmission, allows for planar coordinates to be automatically tracked by altitude. This system can also perform the ISK's role. The IVN, or the secondary indicator with altitude, performs the same function as the IPN. The primary difference is that this system does not include the radial circular sweep nor radar signals. It only displays the secondary air situation, which we will get to in a moment. The secondary retransmission indicator, or IPP, relays targets received via ASPD-1 and allows for affiliation to be transmitted. ASPD-1 interfaces with a teletransmitter, also known as Cabinet R, which encodes data, controls signals, and synchronizes all equipment. Cabinet R also converts code into information that can be transmitted over a communication line. It also controls operation of the primary mixer. Up to 5 indicators can be connected to one teletransmitter, or up to 10 indicators when an item called the SO1 box is installed. Cabinet P, or the teletransmitter, automatically converts encoded messages into voltages that allow the information to be displayed on screens present at each command post. Cabinet H, or the automatic altitude tracking cabinet, is attached to the IPN, and ensures that up to 10 targets can be accurately plotted simultaneously. The interface cabinet is rather self-explanatory. It exists to coordinate the interaction of radar stations and display equipment present at each command post. Cabinet T, also known as the separation cabinet, exists to split information received from Cabinet P into 2 separate channels, ensuring that all relevant data is transferred to ASPD-1 and display systems. Cabinet TS2A performs the same function as Cabinet T, while also providing circuit separation and scale conversion when transmitting coordinates. Each of these cabinets is built on a modular base, and can be equipped with modules to define their purpose. ASPD-1 can receive data from P35, P30, P50, P15, P14, and P12M. Using these radars, information is gathered and displayed to the system operators. ASPD-1 displays planar coordinates, altitude, and affiliation, as well as all commands issued. Each radio technical battalion, which I'll be referring to as an RTB from now on, is capable of contributing 300 kilometers of coverage to the formation. If organized correctly, 1,600 kilometers of overlapping coverage can be established and displayed. Altitude is displayed in 250 meter increments, up to 31,750 meters. The PRV-10 radio altimeter, or P30 radar, are most often employed to determine a target's altitude. The operator can also manually enter altitude, or allow the system to determine it automatically. Alongside a target's coordinates, 10 additional digits are transmitted and reproduced on the screens of each recipient. These digits communicate certain commands or reports on the situation. Each target is denoted by a color which is tied to the subunit tracking it. This allows for easy identification of what is being tracked by each RTB. The number of information sources that ASPD-1 can receive at any given time is 10. Shown on screen is a table of data output discreteness. The speed in which ASPD-1 can transmit and display information to the cascade plotting boards present within each command post is roughly 10 seconds for planar coordinates and 20 to 30 seconds for altitude. The accuracy of acquiring, transmitting, and reproducing planar coordinates is defined by the dispersion radius of the target marks. In a 600 km radius, for example, the root mean square error in the Air Defense Formation command post link is roughly 1.25 plus or minus for a single target, and 3.2 plus or minus kilometers for 6 targets. Altitude is accurately displayed within 125 meters, plus or minus. Data is transmitted in binary at a speed of 60 baud. The time required to transmit a single message containing all relevant target information is 553 milliseconds, meaning 112 messages can be delivered in a single minute. Because the target's coordinates are converted to a unified coordinate system maintained by the command post receiving the message, it is possible to hand off or merge information regarding a single track from multiple command posts. If a command post is receiving data from multiple sources on a single target, up to 12,000 meters in altitude, in 90% measurements, the distance between marks for the same target is about 5 kilometers. Resolution is defined by the ability to observe tracks separately at a 600 kilometer scale. This is 4 to 8 kilometers for Vozdukh-1. A delay of 6 seconds is expected at the formation command post for target acquisition received from RTBs to be registered and displayed on cascade boards. Information received from low-altitude companies is often delayed by 30 to 40 seconds due to reduced automation. The formation command post can process a maximum of 36 to 40 targets on radar, and if more show up, they will have to drop targets, which is a process that involves selecting whichever is least relevant or is being tracked by another formation, and removing them from the scheme so that another target can be added. Radar companies can begin to operate ASPD-1 within 10 minutes upon repositioning. A RTB can usually start the system in 12 minutes due to their reduced staff. The complete time in which it takes for Vozdukh-1 to set up in the field is 20 minutes across the entire formation. This, of course, doesn't factor in the actual movement time, the alignment time, or the setup time for the radars. The indicator screens provided across all of ASPD-1's cabinets are the primary information source for its operators. Here, tracks are displayed, and it is the operator's job to determine if they are false or not. Measurements and transmission of the coordinates plotted on the screen are delivered in 3-dimensional format, so x, y, and height. When information is transmitted using ASPD-1, these coordinates are being reproduced to whoever is receiving them. How this actually works is as follows. Each ASPD-1 indicator displays targets as a luminous point generated by the 45 LM1 cathode ray tube. This functions as a cursor. The operator can move this cursor anywhere on the screen, using a potentiometer. When this potentiometer is engaged, the current running through a deflection yoke is changed using magnetic beam deflection, resulting in the cursor being displaced. This current is called the coordinate voltage. When the cursor aligns with the track displayed on the screen, the operator presses a button and locks the coordinate voltage. This voltage is then translated into a definite combination of pulses, which is fed to a radio station modulator, or data link line, at a speed of 60 baud. Once received, the coded signal is decompressed and converted into a coordinate voltage once again. It is then rescaled to be positionally relevant to whoever's receiving it, so it's not just a reproduction of the voltage as it was initially displayed. Each command post is expected to receive multiple coordinate voltages simultaneously, so a very complicated mixer is present to route them to a larger display system which reproduces each point on the screen to show the location of each track. This is called the overall air situation. Each message delivered by ASPD-1 is broken into 32 positive and negative pulses. This allows for coordinates, affiliation, type of aircraft, armament carried, and more to be enclosed within. Information regarding the target's altitude is always transmitted jointly with X and Y coordinates, as they must be reproduced on two screens simultaneously. Decimal digits are encoded into a 4-bit binary sequence. 4 bits are used because transmitting all digits from 0 to 9 requires 10 combinations. Of the remaining 6 combinations, 3 are used in the receiving equipment for coloring tracks received from different sources. Messages are usually packaged with what is known as a correction burst to synchronize the receivers while the information arrives. This ensures that data is properly distributed once it is delivered. The correction burst consists of 4 pulses whose structure is unchanging. The correction signal is kept small to increase information capacity and reduce transmission time. If any fewer pulses made up this signal, it would increase the likelihood of inaccuracies upon reception and throw off the entire system. And therefore 4 is the hypothetical minimum in which this signal can be transmitted. The first group of pulses in a transmission contain the X coordinate, and the second determines the Y coordinate. The third group has the affiliation as well as the aircraft's model, and the fourth sets the altitude. The fifth handles distribution correction. Each pulse has a duration of 16.7 milliseconds. To reduce errors, a larger number of pulses for coordinate transmission are included, which allows the message to be refined before more complex information arrives behind it. 9 pulses are standard for this reason. Altitude is always transmitted using 128 discrete values. Usually each transmission is 28 pulses long. The 26th pulse carries no information and is always negative, while the 27th and 28th pulses are used to assign reports or characteristics about the target. ASPD-1 employs an array of capacitors as storage for coordinate voltages. There are 28 of these capacitors, and they are referenced as memory cells in official documentation. These memory cells are connected individually to an output circuit. This output circuit serves to encode messages for transmission. While one message is being encoded, another is ready for transfer to the circuit, and while that message is being sent, the message behind it begins to be encoded. This allows for a continuous stream of information. The reproduction process, once information has been received, is carried out using secondary indicators, which I described above. These have a similar deflection yoke when compared to the primary indicators, with the main difference being that high-frequency radar signals are not fed into these indicators. In the decoding channel, the regenerated signal is routed through a set of contacts that are actuated by cams on the receiving distributor. These cams control which circuit paths are momentarily closed as the distributor rotates. The shaft of the receiving distributor rotates at the same speed and in the same phase as the shaft of the transmitting distributor. In addition, the angular positions of the cams on the receiving distributor correspond exactly to the angular positions of the matching cams on the transmitting distributor. This ensures that each received pulse is processed at the correct moment. When transmitting altitude, these cams are split, with one set managing the 5 most important bits present within the height code, and the other managing the 2 least important bits. Separating the last 2 bits improves accuracy, as the second set of cams selects height increments in meters, while the first determines height in kilometers. As each pulse arrives, it's directed to a memory cell within the receiving accumulator. After one complete cycle, all of the 28 capacitors are charged in a pattern that reproduces the received signal. The first 9 capacitors contain the X coordinate, while 10 through 18 denote the Y coordinate, 22 through 28 are dedicated to altitude, and so on. Each of these memory cells are affixed to a decoder corresponding to the value they store. It is stated in many manuals that these memory cells have to be checked often to ensure that they are functioning reliably, as capacitor leakage can have drastic effects on the functionality of the entire system. They are replaced often for this reason. The distributing mechanism of the mixer sequentially sends interrogation pulses to each receiver. If, at the moment of an interrogation pulse, the circuit of the receiver output relay has been prepared by the control channel indicating the presence of a valid information source at the receiver, and the information from the receiver output is fed to the appropriate mixing devices and then to the indicator, information is then routed to the symbol generator, which converts these signals into images corresponding to the target's characteristics. To facilitate the distributor's rotation, an SMV electric motor is present, which allows for speeds of up to 1,800 RPM to be engaged. Motor rotation is actuated through a step-down gearbox. Each revolution takes roughly 533 milliseconds. The distributor contains 40 cam disks, which each engage contacts as it rotates. Each 32-pulse signal can be received in a single rotation. Rotation from shaft A is transmitted through a 1/5 step-down gearbox to camshaft B, which completes 1 revolution every 2,666 milliseconds. Shaft B is used to sequentially pull up to 5 indicators simultaneously in transmission mode. The required pulling rate determines the rotation speed of shaft B relative to shaft A. Shaft B carries 14 cam disks, which, as it rotates, switch specific contact groups in the same manner as the cams on shaft A. In addition to the fast and slow camshafts, the distributing mechanism includes an end distributor, with fixed contact strips, and completes one revolution every 66 milliseconds, rotating at a speed 8 times higher than shaft A. The end distributor has 4 long and short contacts, which determine when pulses are allowed to pass through the system. The distributing mechanism contains what is known as a tachogenerator, which is a synchronous generator with a rotor containing 2 pairs of magnets. It is mounted on the same shaft as the drive motor and serves as a sensing element for motor speed and instantaneous rotor angle. The tachogenerator's EMF frequency is compared to a reference voltage to determine if the motor is operating as it should. This massively reduces errors and ensures the system is operating as expected. When receiving a message, the rotational speed of the motor is set by the frequency of the transmitter's voltage synchronizing upon reception. This is always within 1799 to 1801 Hz. This is managed by a tuning fork on both ends, which is engaged by magnets connected to coils which are charged according to the required frequency, allowing for it to resonate within the expected range. Cascade receives information directly from local radar stations and interfaces with ASPD-1. Alongside displaying information on the ground, it also handles the guidance of aircraft. Cascade guides aircraft using multiple methods. The first is known as pursuit, in which the aircraft is directed towards the target. Intercept, where the aircraft is directed to move to a certain point, and maneuver, where the aircraft follows a certain predetermined route, plotted through what are known as guidance segments. Maneuver is usually employed when surprising a formation of individual aircraft with an ambush from the rear hemisphere. Generally speaking, intercept and pursuit are viewed as extensions of maneuver and are seldom conducted in isolation. Cascade operates in 3 modes when executing an interception, the first being data preparation mode, where all necessary information is entered into the instrument, after which parameters such as the target's flight time, when the controlled aircraft will cross paths with the target, and the course the aircraft should take to carry out the attack are established. To achieve this, the guidance officer enters initial data manually. After determining the aforementioned characteristics, a guidance solution is generated. This mode is technically broken into 2 sub-modes, each generating a guidance solution with a unique equation depending on a myriad of characteristics, such as if the fighter should fly at a constant speed or not. In the third and final mode, Cascade prepares for the interceptors to meet and determines the final point in which the engagement will occur. An important auxiliary mode is Target Designation Mode, which allows the guidance officer to manually set target motion parameters that are otherwise computed automatically. Cascade also features a training mode for peacetime exercises. In either case, Cascade generates the following commands when conducting an interception: interceptor course, speed and altitude, turns, both left and right, and how quickly these turns should be engaged, range to the target, and most importantly, the target's position relative to the interceptor. Additional commands, including when to engage afterburner and when the guidance process has ended and the aircraft are to shift to independent flight, are also included. All of this is managed by a computer made up entirely of a multitude of motors and their accompanying motor shafts, which each correspond individually to a characteristic of the aircraft being guided and the target, such as speed, time to intercept, and position in the air. The speed of these motor shafts is managed by electromagnetic clutches. These motor shafts are recoupled in real time to ensure that Cascade can seamlessly switch from one guidance mode to another. Cascade can handle shifting of one information source to another without delaying the transmission of information to aircraft and command posts on the ground. It takes around 50 seconds to shift between local radar data to ASPD-1 and 30 seconds from ASPD-1 to local radar data. The following conditions are considered the limitations of what Cascade can and cannot handle: flight speed within 500 to 2,400 km per hour, flight altitude within 500 to 30,000 meters, range when operating in a polar coordinate system from P35 to P30 radars, 15 to 380 kilometers, range when operating in a rectangular coordinate system, so when getting data from ASPD-1, negative or positive 400 kilometers, azimuth and target course having no defined limitation, interceptor turn radius with the maneuver method being around 4 to 80 kilometers, length of straight pursuit legs for the maneuver method is 0 to 120 kilometers, duration of instrument guidance by maneuver and intercept methods 0 to 30 minutes, and range to intercept positive or negative 400 kilometers. A single Cascade unit can guide 3 flights of interceptors against 3 targets. Each flight is handled by a separate computer. It is stated that the intercept probability in these conditions is 0.8 to 0.9, radar data depending. Vozdukh-1, with its standard allocation of Cascade, can guide 15 to 18 independent guidance operations, while Vozdukh-1P can handle 6. Cascade operates 6 USDs or data processing equipment sets, which are divided into 2 per guidance channel. Cascade does not control the fighter during its climb to altitude. The pilot independently brings the fighter to the target's altitude in preparation for the attack. Structurally, Cascade's main computing node, or the SRP, is built around 4 servo systems, each using a 2-stage magnetic amplifier and a motor. The amplifiers control voltages proportional to equations required to generate an interception route. Each servo includes a tacho generator for stability. Lazur automatically encodes and transmits guidance commands such as course, speed, altitude, when to execute turns, and target information to the aircraft. It can also transmit interaction commands such as data for adjusting the data link, call cipher, frequency offset number, and more. Lazur automatically receives, decodes, and displays information to the aircraft and its pilot. Lazur can rapidly shift to the reception of information from up to 5 adjacent formations. While each air defense formation has around 8 guidance points, each capable of directing 3 flights, 5 formations operating adjacent to one another significantly increases coverage and intercept reliability across a very wide frontage. Lazur can also receive manual inputs if automatic guidance is unreliable or ineffective. To communicate with Lazur, the R824L radio station is present on the ground, which operates on 118 fixed channels. One R824L radio station has 2 transmitters, mounted on a ZIL-157 chassis. These transmitters operate simultaneously on 2 frequencies rigidly linked to each other by a offset. This is managed by a master frequency generator, designated 2LAU37. These carrier frequencies are positioned symmetrically relative to an assigned communication frequency that is not itself radiated, and is therefore referred to as the quasi-carrier. The offset from the quasi-carrier is extremely stable, and is used as one of the primary tuning parameters for Lazur. R824L is pre-tuned to 6 channels. On each channel, 8 high-frequency offset channels can be obtained. By changing the call cipher on one high-frequency channel, commands can be transmitted simultaneously to 3 interceptor groups. For each air defense formation, 1 guidance channel is allocated. On this channel, an air defense formation using Lazur can carry out the simultaneous guidance of 24 interceptor groups against 24 targets, provided that each guidance point is using a unique offset frequency. Pilots are, before takeoff, assigned the wave, code, and offset for receiving commands from their native guidance point. Throughout the course of an interception, the following commands may be issued. Course from 0 to 360 degrees, which is 128 values in steps of 2.8 degrees, with an accuracy of positive or negative 6 degrees. Speed from 500 to 2,400 kilometers per hour, made up of 32 values, with an accuracy of positive or negative 70 kilometers per hour. Altitude from 500 to 30,000 meters, made up of 128 values, with an accuracy of positive or negative 300 meters. range to the target made up of 4 values, 60, 30, and 15 kilometers, and the cancellation of range commands. Target designation, 3 values, target left, ahead, and right. And finally, turning, which is made up of 3 values, left, straight, or right. Each command cycle takes about 1.2 seconds and consists of 12 code pulses. If 2 interceptor groups are being coordinated, this increases to 2.4, and 3.6 for 3 groups. Each command cycle can consist of the following command sets: course, range to target, altitude; course, range to target, speed and turn; course, range to target, speed and target designation; and interaction commands like wave number, offset number, and cipher number. When 2 different command sets are transmitted, the transmission speed decreases and amounts to 2.4 for one group, 4.8 seconds for 2 groups, and 7.2 seconds for 3 groups. To reduce the pilot's need to constantly monitor guidance commands, audio alerts are provided via his headset when guidance commands change or exceed certain thresholds, such as the course differing by a value exceeding 15 degrees or altitude by a value of 500. As well as the reception of individual interaction commands. To monitor commands transmitted to interceptors, LAU-51 control unit is installed at the command post. It receives, decodes, and displays all commands transmitted exactly as they would appear in the aircraft. Depicted on screen is the operating range of Lazur. A command post designed for interacting with Lazur includes the following elements: 2 LAU-2 encryption device for encoding commands generated by Cascade or commands entered manually by the guidance officer from 2 LAU-1. 2 LAU-1 can communicate with 1 interceptor group and can conduct all of the actions expected of Cascade with the exception of interaction commands. Remote control console LAU-23, which exists to input interaction commands into an encryption device when transferring control of an interceptor to another command post. And lastly, LAU-51 for monitoring the operation of 2 LAU-2 and Lazur. This allows for each instrument inside the aircraft to be replicated and displayed on the ground. AL is the designation given to a system present within each aircraft, intended for reception, decoding, and display of guidance and interaction commands. AL interfaces with the course, speed, and altitude indicators in the cockpit, and indicator lamps where individual commands are displayed. As I mentioned earlier, Cascade provides Lazur with all relevant information, like speed, heading, altitude, and individual commands. On board the aircraft, the 2 LAS-21 and 2 LAS-22 reception blocks convert all this information into coded combinations of frequency bursts. This is processed and turned into electrical signals by the decoding block known as 2 LAS-3. Commands are transmitted in cycles. Each command cycle consists of coded bursts transmitted sequentially, distinguished by their modulation frequencies. 5 modulation frequencies are used to fill the coded bursts. These selected values of these frequencies help reduce the bandwidth of the signal produced during modulation, and make it possible to use a very narrow passband, which significantly increases noise immunity. The duration of a transmission cycle consisting of 12 coded bursts is 1,200 milliseconds. The first 3 bursts form the calling code, indicating which group the transmission is intended for. Burst 4 indicates the number of the transmitted command set. Burst 5 corresponds to target range. Bursts 6 through 12 form the command code. Transmitted commands are divided into 3 sets: guidance commands, interaction commands, and end-of-guidance commands. To reduce the number of coded bursts, simultaneous transmission of commands over 2 lines is engaged using 7 bursts. The 2 binary combinations are converted into 1 quaternary combination. The presence of 7 bursts makes it possible with binary to obtain 128 different combinations. For heading commands, all 128 combinations are used, while for altitude, only 126. Therefore, in the first command set, only heading and altitude can be transmitted. For transmitting speed, 32 commands are provided, requiring only 5 bursts. The speed command in the second code line is formed by bursts 6 through 10. Bursts 11 and 12 provide encoding of turn commands or target designation. Lazur employs what are known as memory relays to store the decoded command until it can be replaced by a new command. Each memory relay corresponds to one digit of a decoded command. They maintain their state until a new rewrite command is issued. In the event that one or more packets are missing during reception, the rewrite relay does not actuate, and the previously stored command remains unchanged. This provides protection against interference or signal loss. LAU-41 is a testing device that exists to check the operability of Lazur. It is usually placed at a distance of 5 meters from the system, after which it runs each relevant block through a battery of tests to determine the existence of any errors. The Formation Command Post has many of the same facilities as what will be described in a moment regarding the construction of lower-level units. In regards to the staff present at this facility, the Chief of Fighter Aviation, the Chief of the Operations Department, the Chief of Intelligence of the Formation, officers of the Fighter Aviation and SAM Troop, and officers of the Navigator Group. Communication within the command post is broken into 4 nets. The first net is that of the Air Defense Commander, for directing the crew of the command post. Included at this level is the Formation Commander and the Chief of Staff, the Chief of the Operations Department, and the Commander of the Radio Technical Brigade. The second net is employed by the Commander of the Brigade to communicate with his subunits. The third net is for the Chief of the SAM Troops to communicate with his forces. The fourth net is used by the Chief of Fighter Aviation. The formation command post of a unit operating Vozdukh-1 and Vozdukh-1P are effectively identical. In both, the most important items are 2 IVN indicators for automated warning of command posts and guidance posts native to the unit, and neighboring formations. The second most important asset is the room housing the ST-35 data link printing system, which transcribes information provided by ASPD-1. Vozdukh-1, in its fixed configuration, primarily employs wired communication for conventional transmissions. This is for good reason, as wired communication can be especially covert, offer high-quality voice transmission, and allow for multiple telegraphs or binarized information to be sent over a single line due to the existence of multiplexing equipment, designated P313 and P314. ASPD-1 can additionally operate through fixed or semi-permanent telephone lines. These lines are set to operate in either telephone or data link mode prior to their application. The formation commander will almost always have access to multiple separate lines, allowing him to communicate with each subordinate command post. Lines will always be provided to allow for expedient communications with neighboring formations as well. In some cases, commanders will have access to direct communication with the Border Guard, Civil Defense, and VMF if they are located nearby. When Vozdukh-1 was first adopted, there were not enough wired communications to allow each formation to employ them. In these early years, an interesting solution was used. Lines would be leased from the Ministry of Communications as an interim solution, while sites were under construction. In some cases, formations equipped with Vozdukh-1 would employ telephone lines belonging to the Ministry of Railways. In some cases, radio relay lines will be used in place of telephone lines. These link all relevant subunits and neighboring formations. Relays are spaced by 50 to 70 kilometers. Most often, R400M, R401, and R401M are used, alongside R405. R400M is a rather powerful relay, around 50 watts. that is most commonly employed by formations equipped with Vozdukh. 5 of these relays can allow for communication ranges of up to 300 kilometers. They feature 12 channels, one of which is multiplexed into 2 data link channels. R401M is a much smaller short-range alternative to R400M. Despite operating at only half its power, just 2 of them can allow for a range of 200 kilometers. The primary downside is that this relay can only provide 2 telephone lines and 2 data link channels. Radio communications are kept to a minimum as they are susceptible to jamming and interception. As a result, they are primarily used to duplicate wired and radio relay communications. Shortwave transmissions are almost always conducted in data link mode, as it increases the range of these messages by a factor of 2. R102 and R820 provide ground wave communications of up to 300 kilometers, and skywave at up to 1,100 kilometers. R102 has 2 data link and 1 telephone channel. R118BM is a medium-power radio station used within Vozdukh-1 formations. It allows for 100 to 150 kilometers of ground wave communication, and 650 of skywave. The R122 is an alternative medium-power station, with a range of around 250. R824, not to be confused with R824L, which is used exclusively to interact with Lazur, facilitates voice communications between ground command posts and aircraft. It can be tuned to 6 frequencies. Guiding aircraft through voice communication is almost always a last resort outside of landing and takeoff, where R821 is used. In a situation where a formation receives information from a distant RTB, a so-called shifted center will be employed. Shifted center processing involves the reception of information and its processing occurring separately. A conditional center is deployed, which serves as an exchange point for information, allowing received data to interface with automated systems when it arrives. This is often employed when there are more information sources than there are reception points. The command post of an RTR, as I will be referring to it from now on, consists of 4 mobile trailers containing all essential elements. These support the Combat Control Group, the Control and Radar Information Processing Group, the Data Transmission Group, the Flight Control Group, and data link/telephone stations. The Combat Control Group is the Commander and Chief of Staff of the SAM Regiment, the Commander and Chief of Staff of the Fighter Aviation Regiment, the Fighter Aviation Navigator, and plotting board operators. The Radar Control Center is staffed by the Commander and Chief of Staff of the RTR, the Chief of Technical Service, Radar Information Processing Officers, Air Traffic Controllers, data link operators, and telephone operators. Present within these facilities, a General Air Situation and Preliminary Calculations Plotting Board, a Flight Control Plotting Board, a Radiation Situation Plotting Board, which may be combined with the General Air Situation Plotting Board, a Data Transmission Plotting Board to visualize communication between the air defense formation, a SAM Fire Control Plotting Board, a plotting board for displaying the movement of missile trains, a plotting board for evaluating the air situation by the Senior Navigator of the Fighter Aviation Regiment, for target designation and distribution of targets among guidance navigators, and control of fighter aircraft are present. Indicators for P-35, P-12M, and PRV-10 used for aircraft guidance are also present, alongside a meteorological display board. Organizationally, a low-altitude radar company consists of a headquarters, a radar platoon, and a platoon for managing automation and communication. Great care is taken to ensure that interference is reduced as much as possible when setting up a radar company. I will not go into detail about the distances in which each asset is separated, but everything is properly spaced and monitored to ensure this is not a problem. Each command post in this unit is powered by a diesel generator. They all have a control room featuring the ISK, 2 interchangeable indicators for altitude input, transmission of reports and characteristics, the primary signal mixer, and the radio altimeter indicator. If the company operates a P-12M, its indicator is installed in the control room next to ASPD-1. Present alongside these elements are manual plotting boards in case ASPD-1 suffers a failure and cannot be operated. Each RTB command post features a control room, an indicator room, a guidance room, the ASPD-1 room, the dispatcher or air traffic control room, the data link room, the telephone exchange room, and separate structures for ventilation, switchboards, boilers, and batteries. The control room contains workstations for the IAP commander and the chief of staff, the RTB commander, IAP and RTB staff officers, the Navigator Group, operators of the general and close air situation plotting boards, and display boards for target characteristics and combat actions. 2 plotting boards are present alongside IVN and IPP indicators. Additional boards are present to display all issued commands and the overall situation within the formation's coverage. Displays to indicate overall combat readiness, meteorological data, indicators for the unit's P-35 and P-12M radars are also available. Plotting boards present within battalion command posts represent 600 kilometers in a 1/500,000 scale. A transparent sheet is placed over these boards which allow operators to draw additional information on top of what is being provided by the system. Plotting boards intended to represent the battlefield or the air situation display 1,200 to 1,500 kilometers at a scale of 1/1,000,000th. Within the formation's command post, a unique 1/300,000 plotting board for displaying targets and fighters moving to intercept them is present. Within the long-range air situation and warning group integrated with the formation command post, a 1/1,000,000th plotting board depicting a 1,500 kilometer radius around the formation for the sake of depicting incoming threats on a greater scale is present. Manual plotting boards are identical as far as scale is concerned with their 600 kilometer automated counterparts. Before Vozdukh-1 can see use, a great deal of preparation must transpire to determine where the formations operating the system will situate themselves. This requires study of the region's topography to determine the optimal location of the unit's radars and command centers. This is important as improper spacing of these elements can generate errors within the automatic command system, causing inaccuracies in data it obtains. As this information collected by Vozdukh is fed to higher-level automated systems for processing before it is then retransmitted to the division, poorly placed subsystems can cause the simulated battlefield environment to look radically different from the actual situation. Radars must also be recalibrated to interface correctly with ASPD-1 after they are repositioned, as their actual polar coordinates are taken into account when determining the location of a target they are tracking. Adjustments will occur every 2 to 3 hours of operation to isolate and correct any errors. Each RTB will establish 10 to 16 alignment points. These are used to calibrate the formation's layout. Proper alignment is enough to remove the vast majority of errors that can be experienced when operating the system. Of course, there have been cases where units have forgotten to account for the curvature of the Earth as well as other factors, but this is negligence rather than the reliability of the system as a whole. And I've only heard of this happening once or twice, when Vozdukh was new and just entering service. While it is unlikely to be done in a combat environment, it is possible to quickly align a formation's radars using an aircraft. This can be done automatically within 3 flights of varying altitudes. To verify the accuracy of alignment, magnetic tapes are stored within each command post, denoting the value the system should be displaying. Measurements are also conducted to establish the track width of each radar, which is factored into the system's calibration. If weather permits it, helicopters may be used for the alignment of a formation's radars, though this is not something that can always be counted on in favor of fixed-wing aircraft. The accuracy of transmissions is assessed using a built-in control that allows for the system's operators to diagnose issues that may be otherwise imperceptible. If the formation has not moved, an autonomous check can be conducted, which will run everything through a battery of tests to determine if an issue is present before operation continues as usual. This is done through the rapid delivery of multiple codes through ASPD-1 and IPN-1, intended to verify the functionality of all transmission and reception equipment, as well as the formation's radars. Vozdukh operates in 2 modes, duty mode and combat mode. Duty mode exists as a high readiness posture prior to the conduct of combat operations. Upon receiving the order to shift to combat mode, ASPD-1 begins to operate. Each battalion command post will begin a mutual data exchange with its subordinate companies to determine if communications are clear and functioning as intended. Upon a target being detected, low-altitude radar companies begin tracking the aircraft with their P-15 and PRV-10 radars. 2 IPNs deliver their coordinates to the battalion command post. IPN-1 delivers the aircraft's polar coordinates, while IPN-2 transmits its altitude. If a large number of targets is detected, the ISK delivers polar coordinates while IPN-1 transmits its affiliation and IPN-2 its altitude. The company commander, via a loudspeaker, instructs the P-15 and PRV-10 radars which sectors they are to manage, and the speed of data transmission they should be engaging. If the target is flying at low altitude, this data is to be delivered immediately. Higher altitude threats are of lower priority, as the battalion has likely already seen them. It is important that data such as the formation the aircraft are flying in and their speed is also provided. The first radar to detect an aircraft is to interrogate it. If the target is suspicious or must be interrogated again by a different radar, the company commander will issue the order. The target will periodically be interrogated as it is being tracked. The operator can manually designate aircraft as well if the system has failed to properly identify an enemy. If the exact number of aircraft in a group is known, for example 3, this data is given manually. If it is impossible to do so, the number and type of aircraft may be transmitted through data link. It is possible to include information such as the weapons likely to be carried by the aircraft and so on. Each track corresponding to a target is tied to an altitude, allowing it to be transmitted with its accompanying information. If the target's altitude is not transmitted for more than 1 to 2 minutes, the operator will receive a warning light instructing him to enter the altitude of the target to tie it back to the track. All of the information presented by Vozdukh's various subsystems can be entered and transmitted manually. A track will be dropped if its last known position is greater than a previously established sensitivity zone. This is usually 10 to 15 kilometers. This is done to avoid targets being mistaken for one another when they cross paths. The target's altitude is automatically tied after leaving the sensitivity zone. Each company can track 10 targets automatically. If a company experiences electronic interference, ASPD-1 will adjust brightness and signal gain to improve visibility. If it is impossible to overcome jamming through this method, the azimuth and width of the affected sector is determined. This is transmitted to higher formations to display where jamming has occurred, and what cannot be seen as a result. If possible, the radar will work to determine the azimuth of the jammer. This is then transmitted as a track within the sector once it has been triangulated. This is done for passive jamming as well. A sector is established and its band is indicated. As the jamming continues, the affected area will be refined every 10 to 15 minutes. Targets entering and leaving the area will be prioritized and intensified by radar companies. Neighboring formations will also work to locate the source of the jamming so that it may be transmitted to the affected formation. During exercises to overcome jamming, it was common to switch the system into training mode and guide an aircraft against an imaginary target to bring the fighter into visual range of the culprit, which was highly successful. When fighter aircraft are vectored against a target, the formation command post specifies the regiment that is to see use, the number of targets, how many aircraft and of what type are needed to destroy them, the route and method of interception, the point in which guidance will begin, and how aircraft are to interact with surface-to-air missiles for maximal effect. This is usually done with pre-generated commands, indicating where the SAM envelope exists and when to break off from the interception route, as to allow for the enemy to be engaged from the ground. Once friendly aircraft enter the envelope, the SAM regiment is tasked with engaging a new target. The SAM regiment is provided with information regarding which target the flight is engaging. This allows for the unit to determine a new target that would not put the flight at risk. If the target is not destroyed, the flight will begin an evacuation with the code Almaz. The SAM regiment, upon an opening presenting itself, is to then immediately fire without restriction. Upon receiving the command to do so, the aviation regiment decides which fighters are to be scrambled depending on its readiness. The regiment's commander will also determine a plan to destroy the enemy himself, which will be sent to the formation's command post and used to effectively guide the aircraft once they are in the hands of Vozdukh. ASPD-1 transmits the position of friendly aircraft and targets they are to intercept. They are continuously tracked by higher-level radars. Early warning radars such as P-12M will continue to observe targets that fighters are not actively being guided against. The navigator, once getting into contact with the formation, refines the plan provided by the regiment's commander. He will then take control of the aircraft and direct them to the optimal position for the engagement to occur, with a significant advantage on behalf of the intercepting party, using all of the information provided by the formation on the state of the battlefield. After a successful interception, the aircraft evacuates the area using instructions provided by the navigator. If it is necessary to do so, the unit can be retargeted against a new, nearby threat. Once the mission is complete, the formation commander receives a new report on his screen, regarding the readiness of the aircraft available to him. Targets are displayed from 0 to 99, and are numbered according to when they were detected. Pilot indices are used to number friendly aircraft. RTBs and local radars surrounding the formation command post exchange information in a very similar fashion when compared to radar companies, and therefore I will not discuss each procedure again. The primary difference is that more personnel exists to verify the accuracy of each track and organize this information. Each track is read aloud so that their location can be plotted on the General Air Situation Board. While all of this transpires, a command post above the Air Defense Division collects information from all formations operating Vozdukh in the area, and establishes a combined picture of the battlefield, which is retransmitted to each division command post, allowing for even greater understanding of the surrounding conditions. It should be noted that in the case of a complete system failure, all of these actions can be done manually. Of course, productivity and speed is going to decrease, but that is expected. While everything is working, it's essential that long-range and short-range radars are organized to provide continuous coverage of the sector Vozdukh is expected to monitor, as a single P-35 radar can only observe a fast-moving target for around 3 minutes while flying at altitude. The guidance zone provided by a single radar is only 14 to 18 kilometers. This coverage is needed for the route to be calculated prior to the interception taking place, and then updated based on the target's position once the aircraft has reached the exchange point in which they are to be handed off for guidance. These preliminary calculations are created using information obtained from the long-range air situation. A myriad of interception solutions are considered and decided upon before friendly aircraft are in control of the formation. This provides some basis to refine how surface-to-air missiles will interact with the flight before the actual engagement. After the fighter takes off, a navigator establishes radio contact and instructs the pilot how he should adjust his lasur for the coming flight, and where the exchange point is located. When the aircraft reaches the exchange point, the navigator switches on the SRP, or the computing and decision device, and puts it into preparation mode. This allows for the exchange of data from the ground to lasur to be monitored for any anomalies. After this, the pilot is given the command Execute Interception by Instruments. This means he will be handing off control of the aircraft to Vozdukh. A successful interception is broken into 4 stages. Stage 1, rapid and straight convergence with the target, a pre-programmed point in which the formation is to break off from this convergence, and begin Stage 2 is established, which is the approach to the rear hemisphere. If the target can no longer be seen by the formation controlling the aircraft, and no other adjacent unit can see it, Stage 3, approach for detection, will begin. If the target is identified, Stage 4, the attack is initiated, which is self-explanatory. These actions are coordinated by the SRP for maximum precision, using information collected by the formation. When the target begins to maneuver, the SRP will compensate, though in case of a sharp maneuver which rapidly changes the speed of the target, the SRP may become disrupted. One of the greatest difficulties for Cascade is varying flight speed. The primary guidance phase provided by the SRP, where the fighter approaches the target and prepares for interception, is broken into two modes, SHR and SHP. The first option allows for the fighter's speed to be set automatically. In both modes, the target's flight time is processed automatically. Both the target and the guided aircraft can have their parameters adjusted manually. In SHR, the system automatically calculates how long it will take the target to reach a certain point. Using this time, the system determines where the fighter should fly in order to intercept the target. If needed, the guidance officer can correct the interception path and ensure the fighter meets the target. In SHP, instead of manually setting the speed, the system keeps a constant relationship between the fighter's speed and the target's speed. The fighter's speed is adjusted semi-automatically, so it always stays a fixed amount faster than the target. This speed is based on the difference between the fighter and the target speeds at the moment the system switches from SHR to SHP. It is expected that SHR will always transition to SHP at a certain point within the guidance process. As described earlier, the system will shift from maneuver to intercept once the fighter has reached a point where it is poised to intersect with the target. After entering its rear hemisphere, pursuit begins, and the target is ideally destroyed. There are, of course, a myriad of factors and equations that must be considered beforehand that allow for a successful engagement to be conducted largely hands-off using Vozdukh. These include the capabilities of the aircraft being guided to the target, the characteristics of the munitions it is carrying, guided missiles or guns, and quite a bit more. I won't be discussing it all in this video, but more will come soon. It should be noted that when the fighter is to engage the enemy and actually prepare for a fight, full control is handed back to the pilot. He is only to offer control back to the ground once the interception has been deemed successful and he is safe to do so. While the aircraft is controlled from the ground, the pilot is able to monitor each action engaged by the navigator. When and if guidance should be transferred to a neighboring unit is decided by the formation commander. While technically the upper limit of simultaneous guidance operations is 18, it is possible using 3 call ciphers to operate 8 guidance points, if we assume that each unit is equipped with Cascade, which is uncommon. In this hypothetical, it would be possible to conduct 24 guidance operations, which means an air army, or an air defense army, could guide 114 flights using 48 guidance points. P-14, P-12M, and P-15 can all be used to direct aircraft, just as P-35 would. There are of course differences, but generally speaking the organization mirrors what was described before. Though when they are employed, a unique problem arises. The possibility of the location of both the aircraft and the target overlapping and being displayed as the same object on the UD screen. This means the navigator cannot ensure the aircraft is actually closed with the target. If the aircraft in this situation has not been already identified, the interception may be impossible. Manuals encourage the navigator to guide aircraft parallel to the target at an angle of 10 to 20 degrees for this reason. This reduces the distance between the target and the fighter at the time of their tracks merging on the operator's screen, so there is a very high chance that the fighter aircraft will actually see the enemy without needing more guidance past that point. One advantage provided by these radars when compared to P-35, however, is a lack of dropouts during turns. This is unfortunately made rather pointless by the fact these radars struggle with maneuvering targets due to how they display information to the navigator. When employing the 250 km display scale, this problem is mitigated, but interceptions usually happen 400 kilometers from the radar, and therefore this is not always possible. This is resolved by the fact that the USD screen's greater resolving power can still track the target and fighter independently. The primary advantage offered by P-14 over P-35 is that it features a larger detection range, making it possible to guide aircraft against AGM-28 or GAM-63 size targets at a distance of 100 to 150 kilometers. P-14 also provides greater range against aircraft flying at high altitude, around 280 to 350 kilometers from the radar, at an altitude of 24 kilometers to be exact. The primary limiting factor imposed by this radar for such targets is the inability of aircraft to actually fly that far without external fuel tanks, and the risk of flying outside the zone in which guidance points can talk to the aircraft. In case an aircraft outruns communication range, it's possible to leapfrog communications with the fighter aircraft behind it, who will relay the messages manually over voice communication. In 1960, V.A. Tarasov met Viktor Mikhailovich when he was giving a lecture on algorithm theory. In the spring of 1961, at the Kiev Higher Engineering Radio Technical School, he was involved in research centered around the integration of civilian computers into automated systems within the military. Around this time, the university had just finished setting up its first Ural-1 computer, which was a huge vacuum tube machine, only capable of around 100 operations per second. This wasn't abysmal for the time, but it certainly wasn't cutting edge. At this time, Laboratory NRL-3 was hard at work developing programs which could be tested on this computer, but it proved impossible to make them compatible with such a dated machine. At this time, testing was centered around data from the Air Defense Command Post being transmitted either by data link or by telephone, after which it would be encoded and transcribed on a tape. This tape was inserted into a computer, which resulted in an alphanumeric printing sequence. After all of the previously described processes were performed, the results were again transmitted by telephone or by data link to the Air Defense Army Command Post, using the ST-35 transcription device. This presented a problematic delay, as aircraft began to get faster. No future automated command complex could rely on analog computers or slow, early digital computers. This was first discussed at a meeting involving the Computing Center of the Academy of Sciences of the Ukrainian SSR, headed by V.M. Glushkov, and the Kiev Higher Engineering Radio Technical School. Integration was noted as the primary issue slowing down the further computerization of these practices. What needed to be studied was the ability for one computer to speak to another automatically without any human intervention over ST-35. In a relatively short period of time, they not only developed principles for interfacing the Ural-1 computer with data link communication channels, but did so using exclusively equipment already available in the troops. This provided a basis to begin improvement and usher in modern digital computing. Recommendations were issued by VM Glushkov at the joint meeting to make maximal use of the existing digital communication equipment already available. Work on this concept would continue enthusiastically day and night. In a conference hall which served as their base of operations, a multitude of bunk beds were dragged inside of it, which would allow them to sleep on site, each scientist catching brief moments of sleep when not working on the project before trading off with his partner. The team was very lucky that the computing center of the Academy of Sciences was headed by Glushkov, and the Higher Engineering Radio Technical School by Rostonov, as they were both firm believers in the technology and enthusiasts themselves. Despite this, the group had to work with a relatively short deadline. As in August of 1961, the 8th Separate Air Defense Army, commanded by General Pokryshkin, was preparing to conduct combat exercises. This was not an official deadline, but the team saw it as a perfect time to test the new subsystems they had been preparing. Debugging Ural-1's integration with ST-35 transpired around the clock. It wasn't before long that everything began to fit together, and it looked like all was working as intended. Trials were finally carried out, and there was a significant amount of excitement shared between everyone there that day, as the software and hardware performed flawlessly. Glushkov was delighted. Everything was in working order before the exercises. 2 weeks were left to train the command post personnel on how everything worked. According to those who were in attendance for the exercises, the complex performed brilliantly. Pokryshkin evaluated the machine's solutions to various problems as they arose, and noted that they were flawless each time. He would see something on the screen, and state, "I agree with the machine's solution." Everyone was satisfied with the results of the exercise, and it was decided to hold a scientific conference. A group of specialists from Moscow arrived for this, which took place at the Kiev Higher Engineering Radio Technical School. Among them were prominent names in the scientific community, such as A.I. Berk and N.P. Buslenko from the Academy of Sciences. Upon the system's demonstration, many in the audience recall the event by stating that the reactions were as if a bomb had been dropped in the room. Afterwards, Berk would go on to say that this was a revolution in computing technology. The computer could receive information from any point on the globe and transmit the results just the same. Despite the low information transfer speed of just 60 baud, this showed tremendous potential. Mikhailovich celebrated for a brief period before immediately preparing for the next innovation using this technology. It was after this that Tarasov arranged a meeting with him. He wanted to report proposals for improving Vozdukh-1 using civilian computing centers and the possibility of creating an information raster recording device based on photographic data link equipment. When this was finally pitched to Mikhailovich, he instantly understood the potential of this concept, and almost immediately began espousing a detailed picture of what Tarasov's idea could become and what work he needed to do to realize that. Alongside all of the existing technology and systems under development in various institutes that he could pull together to make this dream a reality. At the end of this meeting, he said, "Solve all of this. This is your dissertation topic, and the path to solving scientific and practical problems. Good luck. If there is a problem, I will always be glad to help." Tarasov was of course not focused on his dissertation at this time. He was far too inspired to do so. He quickly reported on all that was discussed to the head of the school. Rostonov then responded, "Comrade Captain, I will consider you a very unserious person if next year you do not put a dissertation on my desk." Staving off his excitement, Tarasov worked to complete this first. Mikhailovich was the first to review his dissertation. Afterwards, Tarasov began to grow closer to him, resulting in his appointment to the head of the Laboratory for Command Post Automation. After inspecting Vozdukh-1, Tarasov noted unsatisfactory automation as his primary concern. Interfacing the system with a computer could significantly improve its functionality. As an interim solution, the Ural-1 was once again introduced, as it had already proven itself. Later, a transistorized computer known as UMSHN, which was later designated Dnepr, would take its place. This computer was the first of its kind in the USSR, and was primarily intended for automated processes within various factories, making it a perfect candidate for integration with Vozdukh. When it was originally proposed in 1958, the concept of a computer using semiconductors and ferrite memory on miniature cores was practically unheard of in the USSR. A special engineering department was created with the express purpose of solving this issue, and accumulating experience to build the computer. Organizations that planned to purchase the system were selected by those developing it according to what they could supply in pursuit of its construction. This was done well before development had actually gotten underway. After information about Dnepr's development became known throughout the USSR, various organizations began appearing in Ukraine to negotiate pre-orders. Only the most qualified parties were selected, as the computer falling into incapable hands could discredit its innovative design. This decision was prompted by a myriad of incorrigible figures, like Vozdukh, head of the Computer Technology Department of Gosplan, who had authored many books on analog computing and was actively fighting against digitalization. During a conference to officially approve the development of Dnepr, Vozdukh made an appearance. He was described by those present as carrying himself like a czarist dignitary. Upon hearing that the computer was in the process of being approved, he yelled, "Remove it, so that not a trace remains. This machine is being made for the whim of academics and is needed by no one!" Much to his chagrin, on December 9th, 1961, it was accepted by a state commission, who cited its massive capability leap over analog solutions as their primary incentive. While those who created the computer celebrated, V.A. Zagorsk, who was to supervise its production, in an immature act of defiance, attempted to sabotage its reputation by reporting a myriad of issues that prevented them from being produced. A conversation between Boris Nikolaevich, the computer's creator, and Zagorsk is remembered as follows. "Boris, why do you look so sad?" Boris replies, "In the USA and England, computing technology is already being implemented by those who need it. While here," Zagorsk waved his hand, "I must confess to you, when you handed over the computer's documentation to the plant for serial production, I did everything possible to prevent the machine from entering production." Nikolaevich looked at him in astonishment. "And now, I am ready to kneel before you," he continued, "to ask you to help install the computer in the electroplating shop, and to create on its basis a control system for electroplating automation. I realize that this is very promising." With Dnepr finally in production, it was possible to introduce digital fire control, guidance, and automatic decision-making without human input. The integration of this computer also sped up transmission speed by a significant margin, to the point that those testing the new system noted quasi-real-time display at all command posts simultaneously. Following the combination of a myriad of new subsystems with this computer, what the Research Institute of Automation had before them was a complex unlike anything else in the world. The most advanced ground control intercept and surface-to-air missile control network of its time. In 1971, it was accepted into service under the designation
Прячем ночь под листву углом, за печалью, мне себя совсем не жаль, жаль цветы и дерево, жаль.
There was not an element that had gone unchanged between 1963 and 1971 when Vozdukh-1M finally entered service. Each and every process had been maximally digitalized and automated. Now, VPT-04 was made up of ASPD-1M, APN-1M, Lazur-M, and AS-1M, with APN-1M taking the place of Cascade, Lazur-M taking the place of Lazur, and AS-1 taking the place of Kliech. Like ASPD-1, its more modern counterpart, ASPD-1M, is designed to relay information gathered by radar companies throughout a formation. It interfaces with the same radars, and therefore manages the same coverage. It features an identical transmission speed, and displays altitude in the same 250-meter brackets, up to 31,750 meters. As many capabilities are shared with the older model, one might ask themselves why ASPD-1M is so important. This brings us to the means in which it displays information. This device is known as Strela, and serves as the new and improved indicator screen rolled out with Vozdukh-1M. Strela can receive information from 11 sources simultaneously, and can display a greater level of complexity when compared to earlier methods. Strela can depict 5 control points, all of the secondary information an operator could need for each track, 2 target marks, 2 friendly aircraft, and 2 intercept boundary marks. However, the most important aspect of Strela is that it is not interfaced exclusively with ASPD-1M. It has become a universal display system for depicting relevant information at every workstation across Vozdukh-1M. This is a considerable upgrade when compared to Vozdukh-1, which used a wide variety of unique display systems for every single station. Strela is also ergonomically superior and allows for all relevant information, such as affiliation, symbology, and altitude, to be selected and transmitted faster. Interestingly, in Vozdukh-1M, certain solutions employed within Vozdukh-1 are retained, such as the concept of capacitors serving as storage for voltages corresponding to binarized coordinates. A synchronization process akin to what ASPD-1 engages is still present, but it's been streamlined and no longer involves the same degree of mechanical complexity. Like the synchronization method employed prior, 3 successive pulses are needed to establish contact. This takes about 19 seconds. This is an important methodology, as it is an exceedingly simple way of ensuring that multiple sources can transmit information simultaneously, in real time without interrupting one another, which explains why it was retained. ASPD-1M also uses an identical 32-pulse 5-group transmission method. To display the data gathered by ASPD-1M on a plotting board intended to depict the entire formation's coverage, it is enlarged and projected by a Skiatron CRT known as Xenon. A map overlay can be added to provide enhanced topography and meteorological data. APN-1M serves as the replacement for Cascade, with the bulk of its improvements being centered around the accuracy of commands it can issue, and the complexity of targets it can engage. For example, maneuvering aircraft. The speed of objects it can track and guide against has also increased to 3,600 km per hour, with a closing speed of 7,200 km per hour. It is possible that an error of plus or minus 10 km per hour may be present, as the SRP cannot guarantee complete accuracy. With the integration of Strela, it is possible for guidance officers assisting APN-1M to make decisions faster and issue individual commands with greater speed. With Vozdukh-1M's improved computerization, it is possible to automate the execution of complex maneuvers, such as the Gorka pop-up ambush, which emphasizes low-level flight with reduced radar emissions, until behind the target, in an optimal position to fire. This approach provides an additional reason for the emphasis placed on the dual sensor capability present within MiG-23 and later MiG-25 PD. With the ability for APN-1M to accurately visualize threats and guide aircraft towards them, IRSTs like TP-23 provide silent, GCI-independent search for threats while following the intercept trajectory. Additionally, Vozdukh-1M is capable of assisting the aircraft in generating a 3D track and computed kinematic launch envelope without triggering the enemy's RWR by employing short, low-power ranging pulses every 4 seconds and extrapolating the closure in between, all of which is displayed on the aircraft's HUD. Interestingly, despite APN-1M's modernizations, motors were chosen as the preferred methodology of processing data regarding the position of the interception flight and the target. Mechanism number 8-M, which handles closing speed and distance, is made up of two DABM 16-2 motors. Mechanism number 9M, which displays the angle of the target relative to the interceptor's horizontal axis of flight, is made up of two tracking motors, two tachogenerators for processing the relevant angular parameters, two potentiometers processing sine and cosine, and one potentiometer processing flight time. Mechanism number 10M is identical to number 9M, but uses these components to process vertical flight characteristics. When receiving information from ASPD-1M, a delay of 2.45 seconds is to be expected. An especially interesting feature of APN-1M is the ability to conduct guidance against targets on the ground. This is done by manually entering a false track with a speed and altitude of 0. This allows for the distance to the target and other useful information to be displayed on the aircraft's HUD. This is especially useful for aircraft like MiG-23, which features a fairly simplistic radio-corrected automatic INS navigation system. It is capable of displaying 3 navigation points on the HUD as bank angle and G-force cues. Relying on radio triangulation for navigation resulted in problematic drift rates, requiring frequent automatic correction by beacons. This made such a system extremely useful for increasing the ground attack capability of these aircraft. This, of course, does not mean that MiG-23ML and MiG-23MLA were slouches when it came to air-to-ground. CCIP and CCRP were present, and they successfully demonstrated this capability in Afghanistan. However, the RBSN's success was not the most advanced navigation system out there. The pilot could select 36 additional airbases, but would likely have to go without ILS. LaZure-M is somewhat self-explanatory. It is the new encrypted ground-to-air data link system present within Vozdukh-1M. The most apparent improvement that was introduced would be its accuracy. While LaZure features a discreteness of positive or negative 6 degrees in regards to interception course, LaZure-M has halved this number. It has similarly reduced this figure by 30 km per hour for speed data and 40 meters when concerning altitude. Command set transmission speed is also increased significantly, from 7.2 seconds to 4.5 when directing 3 flights. When transmitting to a single flight, this decreases to just 1.5 seconds. LAU-23M, a more advanced variant of the LAU-23 console, contains 3 20-position switches for selecting one of 20 waves, 3 switches for selecting the cipher corresponding to the order provided by the relevant SRP, and 3 8-position switches for selecting an appropriate time delay. A new guidance mode is provided to Vozdukh-1M, which is used to calculate the fighter's flight time at its initial speed, taking into account the total time balance between the fighter and the target. It is employed to stabilize guidance throughout the second stage, when the fighter's speed is less than or equal to the target speed. It is automatically engaged when the difference between the target and fighter headings are less than 50 degrees. In regards to immunity to electronic warfare, a formation operating Vozdukh-1M can locate 10 jammers simultaneously at any one time. One of the final major improvements would be a greater emphasis on extremely low altitude engagements around 100 meters, which was initially supported by relay aircraft to extend the range of guidance commands. This was difficult with MiG-21, but worked very well with MiG-23. Vozdukh-1M automatically curates and displays the readiness of each aircraft by type and airfield, the readiness of guidance points, the availability of ammunition and fuel, and meteorological conditions at each airfield. Each KH-ZBD screen, which depicts the overall air situation, can display 40 aircraft, the task assigned to each of them, and the actions of those aircraft as they carry out their mission. These are present at most command posts throughout a formation. With all of these new features out of the way, I would like to once again touch on what I believe to be the most striking difference between Vozdukh-1 and Vozdukh-1M. In 1963, the vast majority of jobs within an air defense division were centered around actively engaging in a task assisted by a computer. In 1971, this shifted to supervising a computer as it automatically coordinated the division. This becomes especially clear when inspecting the manual Organization of Combat Operations at a command post of the Aviation Regiment and a Radio Technical Battalion equipped with Vozdukh-1M. It would not be hyperbole to say that this document reads more like a list of what humans are no longer expected to do than how the commander is to organize combat operations. Of course, there are still semi-automatic workstations where human input matters most, such as verifying target information from multiple sources. But I was stunned when I realized that the senior technician's job boils down to monitoring the automatic adjustment process and serviceability checks that are conducted by the system. Following a decision made on October 16, 1963 by the USSR Council of Ministers for Military-Industrial Issues No. 246, NEAM was crowned the leading enterprise in pursuit of developing compact computers for use within aircraft and ATC systems. Almost immediately in 1964, they proposed BEVIM, which soon received the designation Argonne. Argonne was created in stages, the first of which transpired from 1964 into the mid-1970s. This short period of time saw the introduction of 11 unique models, with each variant optimized for a certain task. The first generation of Argonne computers was especially important, as they would be some of the first in the USSR to employ integrated circuits. This allowed for these machines to be much smaller and lighter compared to what had come before, which was extremely important for mobility and use within future aircraft. Due to the need to expedite the integration of Argonne, software compatibility was shelved for the time being. In many cases, it would have actually hindered the series to employ a unified complex instruction set, as it would not have suited the set of tasks expected of each model. To increase the density of each IC, multi-layer printed wiring was used. Manufacturing these multi-layer boards was labor-intensive and involved many complicated processes. In order to shorten development time and reduce errors arising from conceptualizing these boards effectively by hand, software was created and delivered to NEAM, which aided the team. The first batch of computers, those being Argonne-1, Argonne-10-10M, Argonne-11A-11S, and Argonne-12A-12S, employed the new hybrid IC, TROPA. Solid-state models such as Argonne-14 through 17 came about shortly thereafter. TROPA-1 was a product of a joint development initiative between NEAM and NETT. This would eventually give way to TROPA-3 and TROPA-5, which increased BEVIM speed to 200,000 operations per second. Argonne-10 was the first computer to employ this new generation of hybrid ICs, which were standardized on all subsequent models. To standardize dimensions so that production could be automated, 2 printed circuit boards were selected, the first being 230 by 330 millimeters, with 141 leads, allowing it to accommodate 152 hybrid ICs, while the second was 148 by 198 millimeters, with 136 leads. It could accept 96 solid-state ICs. In 1968, NEAM would merge with NIT-SEVT, handing off further development to a new specialized division underneath their new partner. NITSEVT would eventually split off from NEAM in 1986, becoming Research Institute Argonne. To increase mechanical stability, within Argonne-1, Argonne-10, 10M, and Argonne-15, boards were connected by special hinges featuring rubber pads, so that they could be freely rotated to provide easy access to the computer's interior. This simplified maintenance and manufacturing. This was known as a book-type package. To stay thematically on brand with this designation, the rubber pads which housed many of the electrical connections were referred to as the spine. The rest of Argonne's development history is fascinating, as the computers went on to serve in some of the Soviet military's most important automated systems, and were even employed in spacecraft, such as Zond. Unfortunately, these do not concern Vozdukh, and so they will be revisited later down the line. As of writing, it is impossible to tell the exact model of Argonne used within Vozdukh-1M, but my educated guess is Argonne-1. It was released in 1971, which would place it in the perfect time frame for integration with the system a few years after it entered service with Dnieper. It was intended for use in automated command and control systems, and was discontinued the year Vozdukh-1M began to be phased out in favor of more modern systems. Argonne-1 is a single-address parallel operation machine, The computer used a ROM for replaceable constants, has a 24-bit word length, can process 30 instructions, features RAM with a capacity of 512 words, which can be expanded to 1024, has a maximum ROM capacity of 4 by 4096 words for programs and constants, and 64 words for replaceable constants. In the mid-1970s at the Pulkovo airport, the first automated ATC system would be established using Argon-10M as its base. It was managed by Start-P, a system designed to automate the landing of aircraft beginning at 400 meters from the ground. The characteristics of every relevant airframe were retained in memory and employed depending on what was arriving. It could facilitate a blind landing with extreme precision. Start-P would eventually become the subject of a training scandal, after several controllers who did not want to repeat the lengthy equipment familiarization process appealed to the CPSU Central Committee, which almost saw the program cancelled. Despite this, the design team would recover, and the complex would go on to see service in 14 major airfields across the Warsaw Pact. Initially, I assumed that Argon-10M was employed within Vozdukh-1M, but only 20 Argon-10Ms were ever produced, and they were highly specialized for ATC operation. It is for this reason that I am relatively confident that Argon-1 is the computer in Vozdukh-1M, despite Argon-1 and Argon-10M cropping up around the same time in their development schedule, that being 1969, with Argon-10M being delayed slightly until 1975. When integrated with Vozdukh-1M, Argon is capable of autonomously determining the capabilities of fighters to intercept targets, and using this information, generate proposals for the employment of the aircraft available to the unit. The computer works to find the optimal interception point, using the time balance of the fighter and the target, checking the possibility of intercepting the target with the aircraft's current fuel reserve, selecting the optimal flight mode and profile, accounting for SAM engagement zones, finding the optimal closing speed of the terminal phase of guidance, the ideal missile launch range to ensure the target is destroyed, the time required from target detection to missile launch to complete the mission, optimal fuel consumption in afterburner, non-afterburner, and throttle engine modes, and much more. Unlike Lazur, which was entirely made of tuning caps and coils, all of which must be set manually, Lazur-M was fully transistorized and introduces many quality-of-life features that pilots most certainly appreciated. Lazur-M provides 601 quartz-stabilized VHF communication frequencies. For each of these frequencies, 8 channels are available, distinguished by frequency offsets around 88 to 416 kHz. The memory circuits have also seen some improvements, which allows for a greater density of commands to be retained in the event that the aircraft is unable to interact with the division it is attached to for a short period of time. Memory is broken into 2 categories: operational memory and permanent memory. 6 printed circuit boards make up the permanent memory block. On each are 9 bistable flip-flops. Received information is broken into 2 lines of code. Each line is managed by 3 of the 6 PCBs. When information is received, the reset amplifier is triggered by the 2nd and 7th pulse of the message, resulting in the memory being cleared and prepared to store the next command. Operational memory is handled by a nearly identical structure, with the primary difference being that commands are initially decoded as operational memory before being replaced as permanent memory. This allows for 2 commands to be retained sequentially as opposed to the last command retention system present in Lazur. To be picked up by a guidance point, an aircraft operating Lazur-M must not fly below 500 meters. After the aircraft has been captured and command has been established, flying below this altitude should theoretically not break contact. It should be noted that only part of each command is generated on the ground. Once received, they are completed by the aircraft. Lazur-M can provide the pilot with the following commands. Control. Lights up during the functionality check of the aircraft's weapon system using the integral automatic self-check system of the aircraft's weapons. Front hemisphere of attack. Lights up during the instrumental guidance of the aircraft to attack the target from the front hemisphere, and also when the special switch front hemisphere target slow-moving rear hemisphere is set. Automatic. Lights up during automatic control of the radar observation zone, working within the radar operation mode parameters. 100, 60, 36. As the aircraft approaches the target, these numbers display sequentially at the appropriate time during instrumental guidance of the aircraft to the aerial target, and signal the pilot of the approach. Engine operation with afterburner on. This, as the command suggests, lights up when the pilot is commanded to turn the engine to afterburner. Prepare the pilot to execute a turn in any of the directions denoted. Attention lights up when the pilot receives a command via the radio line, informing him that a new task is about to be issued. Attack begins to light up the moment the radar is switched from search and detect targets to automatic tracking of the target. Hill, or Gorka, lights up when MiG-23's computer calculates and issues a command to transition to ascent while attacking an airborne target with R-23 or R-24 missiles. This only occurs if the aircraft is flying at low altitude and expects to ambush the enemy. Missile launch to target allowed lights up when, as expected, missile launch is expected to be effective and destroy the target. Alarm lights up when a command is sent to Lazur to immediately stop the task and return to the airport. Retreat or exit from attack lights up when a command is issued to immediately exit the attack in a safe direction. And radar interference is self-explanatory. It lights up when the radar channel is disrupted. When receiving the front or rear hemisphere attack commands, RP-23 is automatically adjusted to engage the target depending on their range from the aircraft, after which all the pilot needs to do is pull the trigger. This is especially useful when conducting an attack from the forward hemisphere, where the distance from the target and the aircraft decreases rapidly. On MiG-23, these orders are displayed below the HUD, and are therefore always visible. Many of the actions expected of Vozdukh-1M equipped formations are identical to those that would be engaged if the unit was equipped with Vozdukh-1. The key difference is that increased automation and digitalization has allowed for the faster, stealthier, more reliable execution of these actions. While it is theoretically possible in Vozdukh-1, Vozdukh-1M finally provided the ability to reliably conduct an entire combat operation without transmitting a single command over conventional radio lines. The pilot's experience in the air has also been significantly streamlined. Upon receiving the command to do so, he will announce that he is breaking off, after which he will engage the target if he has detected them. This maneuver is repeated by the flight leader's wingman. If the target is not immediately visible, the aircraft is to execute a sustained rolling maneuver with the intention of detecting the target. Generally speaking, it will always be ideal for the aircraft to be guided to a point where the enemy is positioned, in such a way that they are silhouetted and easily acquired. No matter the circumstances, aircraft will almost always fly a course that requires them to turn in the direction of the target, even if an engagement from the forward hemisphere is intended. It is possible that the aircraft will fly a collision course with the target, but this is highly unlikely, as navigators are trained to avoid detection by the enemy until advantageous conditions to begin the engagement are available. As the pilot approaches the point in which he should break off and begin the engagement, Lazur will provide him with the direction he is to turn, the time of its execution, overload, and positions he should be in once he has exited from the turn. While the pilot begins to turn, a tone will sound, which will increase in frequency if the aircraft begins to deviate, ensuring he does not overshoot the envelope in which he is likely to acquire the target. Turning to meet the target is almost always accompanied by a rapid climb and increase in speed. When attacking from the rear hemisphere, it is expected that the target will be detected by radar or IRST, preferably IRST at a distance of 36 kilometers. The Mach 1.8 10-degree climb that transpires before combat is known as Gorka, or hill. This is not an easy maneuver to pull off without burning a considerable amount of airspeed, as this would make intercepting the target impossible. It is possible for the guidance officer on the ground to transmit range data and location of additional enemy aircraft to the fighter, which is displayed on its HUD, vastly improving situational awareness. During the attack, the egress route is preemptively coordinated, so that the pilot can make a quick and timely escape back to friendly airspace if he needs to. If the pilot does not receive an egress route, he will assess the situation before breaking from the engagement and making his escape, until he can be relocated and captured by a guidance point for further tasking. If a new target appears, either while the pilot is en route or exiting from the engagement, his Lazur-M will be tuned to a new command channel, allowing him to receive a new positionally relevant command. To extend guidance range into enemy airspace, a low-flying relay aircraft may be employed. Alternatively, a helicopter or relay balloon will see use. Pilots were fond of Lazur when it was employed. A multitude of testimonies all independently confirmed that pilots wished they were allowed to train with the system more often, and that navigators rarely finished entire engagements without interrupting the automated process by issuing voice commands. It is unlikely that this would be the case in wartime, but for peacetime exercises it seemed everyone was hesitant to employ the complex. It is not unreasonable to assume that this was the result of people not trusting a computer to do their job for them. This was similarly a problem with maneuver when it entered service, and other automated complexes, such as the autopilot present on MiG-23, which could accurately fly the aircraft between guidance points. It could also bring the aircraft in for a landing, with human input only being needed in the final moments, before its landing gear made contact with the ground. As pilots trained to operate without this system, they seldom employed it in full, trusting their own abilities more than the machine. In combat, however, this automation would prove extremely useful, as it would allow for the pilot to multitask unobstructed. Unlike MiG-23's autopilot, in this case, the desire to avoid the computer's input came from navigators and not the pilots, who wished they were able to employ the system more often. This was more common when pilots received guidance from Vozdukh-1 rather than Vozdukh-1M, as the workload to operate the former was much higher, and was likely perceived as too much effort for a peacetime training endeavor involving a small number of aircraft. Vozdukh-1 and Vozdukh-1M were exported to the USSR's allies in Europe. Despite this, the Soviet Union kept the computers they integrated with these systems close to their chest, meaning Warsaw Pact customers had to develop their own computers to operate the complex effectively. Additionally, Poland, who purchased both variants, decided that it would be advantageous to integrate domestic technology to make minor improvements where they saw fit. This never caused any problems, as the core components went unchanged, which was all that mattered as far as integration was concerned. If anything, it is a fascinating demonstration of just how modular the final product was. In place of Argonne, Poland employed Rodan 10, a mobile variant of the ODRA-1325 computer. It was the first ruggedized computer produced in Poland, and would be used in many of its automated systems, including domestic platforms such as RPT-11 and RPT-21, which were integrated at radar command posts. This was by no means a significant downgrade from Argonne. The Rodan series of computers were very capable for their time, and even featured complete software compatibility with ICL 1902 and 1903. Continued investment in this sector would yield the Universal Microprogram Control Unit, or UMJS, which managed to integrate technology that IBM had not yet cracked. But that is a subject for another video. Rodan was unofficially a joint Czechoslovakian and Polish project. Teams from both countries collaborated to improve the computer and realize its maximal potential. This unofficial collaboration was repeated when work began on Rodan 15 in 1980. Poland and Czechoslovakia, for that matter, were especially unique within the Warsaw Pact for their investment in these domestic command systems, many of which existed in the case of Poland, including some very advanced proposals that have not yet been properly documented. NATO's first exposure to Lazur, and by extension Vozdukh, was caused by a tragic accident that occurred on the 6th of April 1966. That day, Yuri Yanov, a senior lieutenant, and Boris Kapustin, a captain, were tasked with flying a brand new Yak-28P from the factory in which it was produced, to an airfield southwest of Berlin. 12 minutes into their flight, while over the densely populated city, both of their engines failed. Realizing that they could not bail, lest the aircraft fly uncontrolled into the heart of Germany's largest population center, likely enacting untold casualties, they decided to attempt an emergency landing in the Spree. After narrowly avoiding multiple residential buildings, they were out of time.
В одной эскадрилье служили друзья, и было на службе и в сердце у них огромное небо, огромное небо, огромное небо одно над моим. Огромное небо, огромное небо, огромное небо.
Upon impacting the Sturtionsee, both pilots were killed instantly. The remains of the aircraft were now in NATO territory, meaning they could inspect a waterlogged Lazur. Yuri and Boris were posthumously awarded Orders of the Red Banner for choosing to die with their aircraft, saving countless lives. As far as I can tell, NATO did not actually conclude anything after inspecting Lazur, nor did they know exactly what it was for. A less depressing incident, also in East Germany involving Lazur, is remembered by a pilot testing low-altitude guidance at a training range. A MiG-23, flying 200 meters above the ground, was mistakenly routed over a small town adjacent to the course in which the aircraft was to fly. Tearing through the sky directly above the village at supersonic speed, the resulting shockwave caused roughly 20,000 rubles in damages. Local authorities did not demand compensation, as a few shattered windows and startled livestock was not terribly concerning. I will now bring this presentation full circle. At the beginning of the video, I mentioned that Vozdukh-1 was a missing link of sorts, a forgotten first investment in automation, the rewards of which the USSR would reap until its eventual dissolution. Really think about that. This was little more than an introductory episode to explain the origins of automated command and control. You haven't seen anything yet.
Сталь сверкает под луною. Тишину нарушить страшно. Так to me. От разбойника лесного не уйти. Эй, рыцарь, он тут как тут. Это славный парень, это Робин Гуд. Эй, рыцарь, он тут как тут. Это славный парень, это Робин Гуд. Эй, рыцарь, он тут как тут. Это славный парень, это Робин Гуд. Эй, рыцарь, он тут как тут. Это славный парень, Робин Гуд. Робин Гуд. Робин Гуд. Робин Гуд. Робин Гуд. Робин Гуда. Пусть попробуют, поймают ветер. Вам любой монах ответит. Тишину нарушить страшно. Talk to me. От разбойника лесного не уйти. Эй, рыцарь, он тут как тут. Это славный парень, это Робин Гуд. Эй, рыцарь, он тут как тут. Это славный парень, это Робин Гуд.